In this class, we're going to consider finding the area underneath a curve. So first of all, what do we mean by underneath a curve? Well, the scenario we're looking at here is that if you graph a function, so if you've got a curve represented by some function, let's say f of x, so something like, say, this. So this would be your y equals f of x. Then if you take two x values, which we're going to call the limits, and let's just call those x values a and b. So let's say a is here and b is here. If we draw on a little sort of construction line up there to give this kind of sort of shape here, then this area in here, that is what we mean basically by the area underneath a curve. So it's the area under the curve, so under this part, like the actual curvy part, between the two limits and bounded by the x-axis. Now, obviously that shape there, like especially the curvy part, is not some regular shape. It's not like a cuboid or a prism or something like that. It's going to change depending upon the function, like these different examples here obviously are very different types of function. So it might not be, or it is not obvious how we go about finding that area. And indeed, this is one of the classic great problems in calculus from hundreds of years ago when we were just figuring out calculus. How do you actually find that area? There must be some relationship between the function itself and that area. Well, the approach that we basically take is to do with a Riemann sum, as we've seen maybe already in this series. If you've already watched those videos, we kind of imagine like chopping this up into little rectangles. So we make like subdivisions, and then we imagine shrinking those rectangles so that they're almost like infinitesimally sort of thin, so that we're not just making an approximation, but we're actually representing the limit. The actual area by using a limit. And it turns out that when we do that, and we add all of those rectangles up, taking the limit of that summation of all those rectangles, well, that is the definition of an integral. So it turns out that basically the area, that shaded area, incredibly conveniently is just represented by the definite integral between a and b of f of x dx. So we're not going to worry too much about the mechanics of where this, what the derivation of this is, where this actually comes from. It's kind of already been looked at in the Riemann sum videos, which appeared earlier in this series. But it's a great result. It's a really powerful result because we already know how to do definite integrals. We've been working with those already quite a bit through the improper integrals and just working with definite integrals themselves. So we hopefully have got a bit of experience of these already. So you can actually find these areas very quickly just by taking the definite integral and evaluating the number that you get. So that's the scenario here. Let's look at a few examples. Now, depending on the question, that could be presented in different ways. So you might see f of x functions, you might see curves represented by y equals, and the same with the limits. The limits might be given as these sort of a closed interval like this, so between 1 and 3. That means including 1 and 3. If you've got an open interval, that would be written 1, 3, like that, and you would not include the 1 and 3, but that's not relevant for this. So it could be presented like that, could be represented as a range of values, could be represented as a graph as well, and it could actually show you the area that you've got to find the numerical value for. So different ways to present these, but essentially we're just going to set them all up as a definite integral and make the evaluation. So this one here, the area between that curve, the x-axis, and these two values here will be represented by the integral between 1 and 3 of that function there. So minus 3x squared plus 17x minus 10 dx. So we just simply need to work through the mechanics of this. So this is already in an integratable form. It's a polynomial. We can use the power rule. So we can go straight to putting this in our sort of square brackets like this, just using our normal normal definite integral, not differentiation, normal definite integral technique, increasing the power by 1, dividing by the new power. So it's going to give us minus x cubed plus 17 over 2 x squared minus 10x. So not the prettiest thing here. It's going to be a little ugly when we come to evaluate this, but that's often the case, especially with fractions. In fact, this one's not too bad because we've only got one fraction out of the 3 terms. It can be a lot worse than that. So that's the scenario we've got. We need to sub in our limits. So remember to sub them in very carefully because you're going to be subtracting the second limit from the first. So definitely use brackets for this. So 3 to the power of 3 is 27, so it's going to be minus 27. 3 squared is 9, so we've got 17 times 9. So just thinking about that, you've got 7, no, that looks like a, I don't know what that looks like, a pi or something. That's actually a 17, so 17 times 9. So that's going to be 90 plus 63, which is 153. So that second term is 153 over 2. That's the kind of thing that can get thrown up in these questions. So be prepared for that. There's some ugly numeracy sometimes. And then 10 times 3 is 30. So it's going to be minus 30. Subbing in the 1 should be a little easier. So we get minus 1. We get plus 17 over 2. And then minus 10 like that. Personal preference as to how you evaluate this. Personally, I like to gather together the whole number terms and the fraction terms. So you've got these two fraction terms that will combine. So what I'm going to maybe do is just take a line maybe to simplify each of the brackets. So we've got these two whole numbers that could go together. So that's minus 57 plus 153 over 2. There's no real correct process for evaluating the numerical part. Just whatever is going to work for you, whatever reduces the chance of making a mistake. Minus 1 minus 10 is minus 11 plus 17 over 2. Then we've got minus 57 minus minus 11, so that's plus 11. So minus 57 plus 11 is going to be minus 46. Then we've got 153 over 2 minus 17 over 2, so it's going to be minus 1, sorry, it's going to be plus, we're taking 17 off of the 153, so that's going to be 13, let me think about that, that's going to be 136, I believe, over 2. Let me just check that. 136, 146, yeah, I think that's right. Okay, so just seeing if we can take this a little further. It's quite common to end up with a whole number and a fraction term. Sometimes, usually we can then just go and merge them. Sometimes these will be calculator questions. Quite often actually you can just fire it all in the calculator, but you probably want to work it forward a little before you do that because it's quite a lot to put in the calculator maybe in one go. This second term here, I think we can actually divide by 2, so that's going to be 68, I think. And then 68 minus 46 is 22. So that area represent, well, we don't have a graph, but that area represented by this definite integral is 22. And there's generally no units in these questions, but it is an area, so maybe just write it as units squared or square units, or sometimes these questions are contextual and you will have some kind of unit. If not, unit squared, something like that. So yeah, this part in here can be a little fiddly with the numeracy, especially if you've got multiple terms to deal with. Sometimes it's a lot easier. This one will probably be a bit easier. Really just depends. You'll need to gain a little bit of experience with those as to know how to evaluate them. But this part, the mechanics here, it should be fairly familiar to you. Okay, so looking at this one, first of all, we see that this is not in an integratable form, and we know we're going to have to integrate, so we may as well go ahead and use our indices rules to put that in an integratable form. So the area represented by this function and the x-axis in between these two limits, that area would be represented by the integral between minus 4 and minus 1 of 5x to the minus 2 dx. Okay, so just one term here to integrate, so that's quite convenient. So we can just go straight to putting this in the square bracket, minus 4 minus 1, increasing the power by 1, that's going to go up to a minus 3, dividing by that new power, so we're going to get minus 5 over, increasing the power by 1 is not going to go to minus 3, increasing the power by 1 is going to go to minus 1. So let me actually just amend what I was about to write there. I took 1 off the power, didn't I, taking it to minus 3. So this is going to be increase the power by 1, which goes up to minus 1. divide by the new power, so that's just going to be 5 divided by minus 1, which is just minus 5. So just check my working with that, but that is how, hopefully, I think if I got that right, that's how it comes out. So increase the power by 1 up to minus 1, divide by the new power, and you end up with that guy there. So just processing the numbers now. So maybe actually, we might just take a line to rewrite that with a positive power. So it's going to be minus 5 over x to the 1, or just minus 5 over x, between minus 4 and minus 1. Then we can go ahead and sub in those values. So subbing in the minus 1 would be 5 over minus 1, but there's already a minus there, so it's affected by a double negative. That term then just becomes 5 over 1, which is just 5. Second term is minus 4 being subbed in there. That's going to be a minus 4, so that'll be a positive, but the rule, remember, is to take away that second limit, evaluated second limit. So that's going to be, effectively, that's a triple negative. It's going to be a minus there, but the overall thing's a minus, so that will end up being a negative, and it's going to be minus 5 over 4. Okay, so you might write your final answer here as a decimal if it's a calculator question, or you could just make the 5 into 20 over 4. So 20 over 4 minus 5 over 4 to give us a final answer of 15 over 4. And again, it represents an area, so something like square units or unit squared, just to write that as your final answer. Okay, cool, right, so that one, smaller integrand there, but introduced a non-integratable form. That's true in all integration, doesn't matter what kind of question it is, you've always got to look out for that. Same here, this is not in an integratable form, so just put in this, make some space here, just putting that into an integratable form by multiplying out the bracket. So y equals x cubed minus 2x squared. So we're just going to set up our integral here between 0 and 2. So integral between 0 and 2 of x cubed minus 2x squared dx. So not too bad, again a polynomial type function, a little bit like this one over here. So it should be reasonably straightforward to evaluate, only 2 terms as well, so it shouldn't be a terribly ugly thing to deal with. So it's in an integratable form, increase the power by 1, divide by the new power using the power rule, so we get x to the 4 over 4, and we get minus 2 over 3x to the 3, evaluated between 0 and 2. It's always good when one of your limits is 0, because for polynomial functions, that means you're going to get a lot of 0 terms, and that actually happens quite often, so that's a very useful thing, especially if it's a non-calculator question. So subbing in the 2 first, so 2 to the power of 4 is 16, 16 divided by 4 is 4. So that first term would be 4. 2 to the power of 3 is 8, 8 times 2 is 16 over 3, that's going to be 16 over 3. Subbing in the 0, we're going to get 0, and we're going to get 0, so we're just going to be basically subtracting 0, which obviously we don't need to put in, but we'll just put that in anyway. And just taking this forward, let's make this 12 over 3. So 12 over 3 minus 16 over 3, which comes out to be minus 4 over 3. Now, bearing in mind that what we're trying to do here is to find an area, we're trying to find like an area like this. This should raise a few alarm bells because it's come out to be a negative. Now, obviously, in the dimension that we live in, we can't have negative space, or maybe you can, I don't know, I don't take physics, but maybe you can't have negative space. But anyway, in our math questions, we're looking for a positive answer, but we don't always get a positive answer, and it seems a bit contradictory. But let me just quickly explain what has happened here. If you look at the graph of this function, it basically goes like this. It's a polynomial, a cubic, it comes up like that, and it turns at 0 and then goes up like that. So this point here is at 2, the x-intercept, the root. This point here is at 0. So the area that we were representing here by our integral is actually this area here underneath the x-axis. So although we use these definite integrals to represent areas, they're sensitive to their location in the coordinate axis. So basically, if the part of the graph that you're interested in, like this one, is underneath the x-axis, so Remember, this is our x-axis here, obviously. So if you're underneath, when you take the definite integral, it will evaluate to a negative number. But because we're interpreting that integral as an area, it does represent the area, the numerical value itself. We basically, when we come to write the area, we just say that the area equals 4/3 units squared. And we just basically ignore the fact that it's come out to be a negative. So look out for that. You'll see that quite often. And if you've got access to the graph of the function, if you knew ahead of time there was that area there between 0 and 2 underneath the x-axis that you were going to be finding, then that should already tell you to expect to get a negative number here. In fact, that would help validate you've done it correctly. If it was that area there and you worked through all of this and this came out to be positive, that's definitely not right because they're always negative. So if you're above like this, it'll be positive. If it's an area below, like this part here, it comes out of the integral as negative, but we ignore the negative when we write the area. So that's really the only kind of caveat, the only little thing to look out for in these questions. Otherwise, it's just setting it up like this. So set up your original definite integral, working through the mechanics, doing the numeracy part, which can be a little bit cumbersome, and then getting your final answer. So hopefully that makes sense. We've already worked a lot of these definite integrals so far in this series in Calculus 2. So the technique itself should be fairly straightforward here. It's just maybe a new interpretation, although we have already alluded to the fact that definite integrals represent areas. In the next class, we're going to take this a little further, and we're going to look at the area between two curves. So if you had, for example, a function whose graph went like this, and another function whose graph went like this, we're going to look at the area bounded between those two curves rather than bounded between the x-axis and the curve. The mechanics of doing that is fairly similar. So once you're happy with the material in this class, you can just move on straight into that next class.